carbohydrates. And we're not going to introduce that many new reactions in this chapter. It's mostly going to be about structure. And I want you to know enough that you can look at a carbohydrate and say what it is, and that you can look at a more complicated carbohydrate and say what the connection between individual sugar subunits of that more complicated carbohydrate are. So we'll take you through the carbohydrate structure, some of the reactions that they can do, and we probably will just spend today and Monday on that. So to begin with, you've seen glucose before, and you've answered questions before on exams about converting a cyclic hemiacetal into its open chain form. And in some cases, opening up a cyclic hemiacetal, that part was easy. Getting the right stereochemistry when you redraw it was the hard part. This molecule is called beta-D-glucopyranose. That's its technical name, though sometimes people will look at that and they will just call it beta-D-glucose. Technically, D-glucose refers to the open chain form. And that open chain form is here. You can draw it still in this sort of chair shape. We'll keep everything else in the same place. The only thing that changes is that C1 here is a hemiacetal and C1 here is an aldehyde, whereas the oxygen on C5 is participating in that hemiacetal here, but in D-glucose, the open chain form, that's an OH group. Okay, so beta-D-glucopyranose is a cyclic hemiacetal, and the open chain form and the cyclic hemiacetal form are in equilibrium in aqueous solution. We'll talk about that in a minute. But before we do that, I want to talk about each portion of the name and what it means. So, starting out with D, D refers to stereochemical configuration at this stereocenter, C5. We're going to be dealing in this chapter, and we're not going to read the whole chapter. There are carbohydrates that are shorter in length than 6 carbons. But we're going to stick to the 6-carbon carbohydrates for the most part in this class. So there are 1, 2, 3, 4, 5, 6 carbons. Carbon 6 is a CH2 group. It's not a stereocenter. So C5 is the stereocenter. This group that's coming off C5 is a CH2OH group. Another term for that is hydroxymethyl group. So you'll hear me talk about the hydroxymethyl group on C5, so you should know what I'm talking about when I say that. D configuration, when you draw the chair structure of glucose in this way, means that the hydroxymethyl group is up at C5. Now, are you guys still okay on chairs? You still know axial versus equatorial? You still know up versus down. You know axial doesn't always mean up and equatorial doesn't always mean up or down. Yeah, go ahead.
So is it up and axial or up and equatorial?
So the hydroxymethyl group here would be equatorial and up. Yep. Okay, so D sugars have, when drawn this way, have up configuration at that C5 stereocenter. Okay. Okay, what does the beta mean? This is a little bit tricky. When drawn this way with the C5 group equatorial up, beta means that this C1 hydroxy is also equatorial up. Another way of saying this is that beta means that the C1 hydroxy and the C5 hydroxymethyl are cis to each other. Okay? So beta refers to the stereochemical configuration of atom 1. Now obviously we could do R and S for all of this, but biologists generally don't. And so we're learning to talk the chemistry, we're learning to learn the language of biochemistry so that when you take 481, you can understand what's going on. Okay, so when the hydroxymethyl group on C5 and the OH group on C1 are, and I guess I should have highlighted the carbon instead of the OH group, when they are cis to each other, there we go, the configuration is beta. If they were trans, if C5 is up and C1 is down, that would be the alpha configuration. So let me draw real quickly the alpha version of glucopyranose, alpha D glucopyranose. You're going to draw this exactly the same way, only at C1 the OH group is going to be down, axial, instead of up, equatorial. And again, you can see that the reason this molecule is alpha is because the C1 OH group and the C5 hydroxymethyl group are trans to each other. Okay, so that's the beta part of the name. You will see later on that the alpha and beta forms of glucopyranose are actually in equilibrium with each other, and we'll talk about their relative stabilities. For right now, what is the stereochemical relationship between the alpha and the beta versions? What would you call them? Diastereomers. Good. Remember that stereoisomers have the same connectivity, but different configuration of the groups. Remember that enantiomers are mirror images, and remember that stereoisomers that are not enantiomers must be diastereomers. I saw a hand. Go ahead.
If it's a different configuration, wouldn't the other OHs, other hydroxy groups be differently arranged?
No, not necessarily. So I'm referring to the different configuration at C1 and only at C1. So stereochemistry at C2, 3, 4, and 5 remains the same. There are a lot of ways to be a diastereomer, right? An enantiomer must, if we were to draw the enantiomer of this beta-D-glucopyranose, it would have opposite configuration at each and every stereocenter. If it had opposite configuration at all of them but one, that would be a diastereomer. And if it had opposite configuration at one but not all, that would still be a diastereomer. In other words, enantiomers have opposite configuration at each and every stereocenter. Every other kind of stereoisomer is a diastereomer. Yeah?
What's the difference between a diastereomer and a constitutional isomer?
Diastereomers have the exact same connectivity, and constitutional isomers would have different connectivity. In other words, if I moved this oxygen over to make an ether there and a CH3 group there, that would be a constitutional isomer, totally different molecule. Yeah?
If the alpha means that the C1 and C5 groups are trans to each other, could the one be equatorial up and 5 be axial down?
That's right. Could the one be equatorial up and the 5 be axial down? Yes, though that would be L configuration at C5. Yeah. One thing I should mention is that most sugars in biology have this D configuration at C5. Not all of them. There are a few that are L, but for the most part, they're D. And we won't actually deal today with learning names of L sugars. Other questions? Okay, there are 1, 2, 3, 4, 5 stereocenters in glucose, 2 possible configurations at each stereocenter, 32 possible stereoisomers, 2 sets of 16 stereoisomers where the pairs are enantiomers of each other. We're exclusively going to deal with the D side of that, okay? And among all of those 16 diastereomers, we're only really going to learn 4. So, yes?
Is there a relationship between R and S and L and D?
Is there a relationship between R and S and L and D? No, it's a good question. The D and L, and I should know the science on this, but it's like a whole long time ago, and it's hard to care after a while. But so back before we had modern techniques for visualizing molecules and establishing their absolute R versus S configuration, you could tell the difference between two enantiomers by optical rotation, and you could also crystallize two enantiomers separately. That's a long story, and it has to do with the two crystals are actually, well, anyway, I don't know whether to say more about that or not. But anyway, there were forms of simpler molecules that they used to establish these two are enantiomers, and the one that rotated light in the right-hand direction was called D for dextrorotatory, meaning right-hand side, and the one that rotated to the left was called levorotatory, or L. And so that's optical rotation, which you learned about in 351. Those simple model compounds, they were then able somehow by analogy to assign stereochemistry to larger compounds, often by degrading the larger molecules into the smaller ones. And so for a while, I think the original absolute configurations were like D and L glyceraldehyde, and if you had the similar stereochemistry to D-glyceraldehyde, you were called D. So that's where it originally came from. We still use it for historical reasons, but it doesn't really have anything to do with R versus S. For us, D is, you'll be able to tell it's a D sugar because it's going to have this configuration at C5. Yeah. Okay, yeah.
Stereoisomers, is there like a certain percentage that they're formed based on stability?
Is there a certain percentage of stereoisomers that are formed based on stability? These two? Yes, and we're going to talk about that. These two diastereomers interchange with each other chemically. Others don't. And the fact that these two can interchange has to do with the fact that C1 is a hemiacetal. We'll talk first about that process, then we'll talk about maybe some other stereoisomers. A little bit of terminology, go ahead.
I might have misheard this, but is the equatorial and up referring to the hydroxymethyl group, or is it referring to the...
Yeah, the equatorial up refers to the hydroxymethyl group, but it's also true for the OH group in the beta anomer because it's cis to the hydroxymethyl group. Okay, a couple more terms. A diastereomer that differs at one and only one stereocenter we have a couple of special terms for that. One is epimer. So the alpha and the beta diastereomers are C1 epimers of each other. They differ in stereochemistry at C1. And we have a special term for epimers at C1. We will call those anomers. And the carbon, C1, we will call the anomeric carbon. That is the same thing as calling it a hemiacetal carbon. So I will call beta D glucopyranose the beta anomer. I will call alpha D glucopyranose the alpha anomer. It would also be appropriate to call these C1 epimers of each other, or the alpha epimer and the alpha or the beta epimer. Okay, a couple more things about the name glucopyranose. The os is the ending for a carbohydrate. Any carbohydrate is going to have that os ending. Pyran refers to, I'm running out of space for making notes here. Pyran refers to a six-membered ring containing oxygen. And you can see that in this hemiacetal form, you have a six-membered ring that contains oxygen. Lastly, gluco refers to configuration at C2, C3, and C4. When in this, and glucose is the easiest one to memorize because when you draw beta D glucopyranose, you draw a chair with an oxygen in it. There's OHs on 1, 2, 3, and 4, and they're all equatorial, and then you've got a hydroxymethyl group on C5. when C2 is down, C3OH is up, and C4OH is down, this sort of down, up, down configuration, that's where gluco comes from. Yeah?
So gluco is 2, 3, 4, and all of them are equatorial with the ups and downs alternating?
Yep, that's right. Gluco is 2, 3, and 4 are all equatorial when drawn in this chair, when drawn in this most stable chair, and they're alternating down, up, down. Yep. Okay, yes?
So they can alternate the other way, or it's just that way?
So it's just this way. When I draw it in this chair form, the OH group is on C2 is down, the OH on C3 is up, and the OH on C4 is down when I draw it from this perspective. It gets a little tricky to make absolute statements like that because I could pancake flip the whole molecule and then the down-up stuff would be switched. It would still be the same molecule though. Okay, so let's now talk about interchange. Well, let's talk about ring opening and interchange between alpha and beta anomers. So let's redraw beta D glucopyranose and let's show you how ring opening happened. And this will be a review of things from, drew it too far over. This will be a review of things from chapter 14. When we showed opening of a cyclic hemiacetal in chapter 14, we frequently showed first protonation of the ring oxygen with some acid catalyst. Probably even the small amount of H3O plus that's present in water is sufficient to do this. Ring opening, if you recall, because our goal is to get to this form in which the C5 hydroxyl is free and C1 is an aldehyde. Ring opening needs to involve kicking off of the C1 oxygen. Sorry, I'm saying this wrong. Ring opening needs to involve kicking off of the C5 oxygen as a leaving group by the C1 hydroxyl as a kicker offer, and this is sort of your carbonyl carbon here. The problem, of course, is that a neutral oxygen can't kick off a negatively charged oxygen. So we had to protonate that oxygen first using an acid catalyst, and again, the small amount of hydronium present in aqueous solution at pH 7 is probably sufficient for this to happen. Once we protonate that hydroxyl, it becomes a good enough leaving group to be kicked off by the neutral C1 hydroxyl. So then we're going to have lone pairs on the oxygen kick down and kick off the leaving group. That will get us to this. That's kind of fun, isn't it? That'll get us to this intermediate oxonium ion in which the carbonyl oxygen is protonated. And then getting to the final ring open form is going to involve the conjugate base of our acid removing the proton to get to the aldehyde. I'm going to slide the aldehyde over because that feels a little crowded. Okay. So that's ring opening as you saw it in chapter 14. That should be mostly review. You use an acid to protonate the OH group and protonate the ring oxygen, turn it into a good leaving group. You use the conjugate base of your acid to deprotonate the aldehyde in the oxonium ion. Now, a colleague actually showed me an alternative that makes a lot of sense and which I want to show you because it illustrates how these things can happen not only in water but also in enzyme types of mechanisms. So I meant to write ring opening mechanism, but I wrote mechanism too early. Oh well. Ring opening mechanism. Here's an alternative. If you look at the structure of beta D-glucopyranose, and if I take this OH group here and then draw the hydrogen out like this, you can sort of see how I've got 1, 2, 3, 4 atoms starting to form a new chair. And if I put an oxygen from water here, and the hydrogen from water there, I sort of complete a 1, 2, 3, 4, 5, 6 chair-shaped ring. And in that process, a single water molecule, because six-membered arrangements of atoms place 2 atoms close together to each other, this oxygen close to this hydrogen, then this oxygen close to this hydrogen, you can actually have this single water molecule act as both acid and base. So in the same step, you can show this oxygen removing this proton. Then you can show the electrons from this oxygen-hydrogen bond attacking and removing a proton from that hydroxyl group at the same time as you show the pi bond forming, at the same time as you show the kicking offing happening. Yeah?
I think on one of your formations up, you have a hydroxy group and one in the middle there.
Oh yeah, thank you for that, sorry. I meant to draw hydrogen and then my brain did. Yep, thanks. All right, so this is an alternative mechanism for ring opening. You can certainly draw it this way if you want to. It illustrates how even a single water molecule can act at the same time as both acid and base. And these reactions, these types of things where water acts as both acid and base in the same step often occur when you can form a 6-membered ring. That would take you, if you follow the arrows, that takes you in a single step to the ring opened product. All right. So that's ring opening. Now let's talk about interchange between the alpha and the beta anomers. It turns out that you can interchange between alpha and beta anomers via the ring opened product. So what I'm going to do now is just repeat this. So I want to display it separate from that alternative mechanism. So this is ring opening. And you've seen a couple of different mechanisms for that above, so we don't need to repeat it. But you could see that if I rotate around the bond between C1 and C2, oops, suddenly had an eraser. Rotate around the sigma bond between C1 and C2, that would shift the aldehyde into sort of a down position. And then you could imagine ring closing from that other shape. If you wanted to show this all with the same water molecule, you could do it like this. You could show water acting as a base to remove this proton at the same time as the bond between the oxygen and the hydrogen's breaking and the electrons are moving onto the oxygen. We attack the C5 oxygen attacks the C1 carbonyl at the same time as the pi bond is breaking, lone pairs on the oxygen attack this hydrogen and electrons move onto the oxygen. You could show ring closing in that way. And that would lead you to the alpha anomer. Of course, you could also show ring closing via the stepwise mechanism that we've used before. This process of going from the beta anomer to the alpha anomer is called mutarotation. Mutarotation, because it's not actually a rotation, you can't get from the alpha and the beta anomer simply by rotating around carbon-carbon bonds. You have to break bonds, but you open up the ring, rotate, and then close the ring back up, and then you get the alpha anomer. Questions about that? Yeah?
Is one way more correct than the other to say a stepwise versus a single step?
No. Is one way stepwise, like shown here, versus a single step more correct than the other? No. And in fact, it's also, I've involved both bonds and lone pairs, but you will see some organic chemists, instead of doing what I've drawn here, will do this. Let me just simplify it a little bit. They'll show just 3 arrows like that, and that's fine too. Conceptually, that's exactly the same. I kind of like this one because it allows you to at least have a place to begin with lone pairs. But anyway. Okay, mutarotation is interchange of the alpha and the beta anomers. Now, there is another alternative for mutarotation, and it's important too, and will help you remember some things about hemiacetals. So, alternative mechanism, it's not an alternative to mutarotation, it's an alternative mechanism for mutarotation. So, starting with the beta anomer, you can say, what if our acid catalyst, instead of protonating the ring oxygen, protonated the OH on C1, thereby turning it into a good leaving group? Now the OH2 plus is a, oh shoot, I forgot to, there we go. Now the OH2 plus is a sufficiently good leaving group for the neutral ring oxygen to kick it off. And the intermediate that's going to be formed is here. You'd have a pi bond with oxygen and carbon, and a positive formal charge on the oxygen. Okay, and this is called an oxonium ion. Now, before I get too far, this is how we've always done chemistry with hemiacetals. But your text will do something different that's going to be somewhat confusing to you, so I want to clear it up here. What your text will show is fully equivalent to what I've drawn here. Let's make sure I got a little bit more room. Instead, your text is going to draw that same intermediate with the protonated OH2 group. But instead of having lone pairs act as kicker-offer, your text may show the OH group leaving. Now, some of you are going to worry about the distinction between what I drew up here, where the lone pairs on the oxygen are the kicker-offer, and what I've drawn down here, where the OH group just up and leaves. I'm going to argue that there is no distinction, that those are exactly the same mechanism. The reason I'm going to argue that is because they lead to two resonance structures of each other. Remember, the oxygen has two lone pairs. Up here, one of them kicks down to form a pi bond. Up here, it doesn't, and the OH group just leaves. But notice that these two, running out of space. It doesn't matter. I'm trying to keep everything on one page because when I export to PDF, that was a weird way of saying export. When I export, nobody says export. When I export to PDF, if it straddles the page, then it sometimes gets hard to read. So, okay. Meter rotation. So what we've drawn here are two equivalent mechanisms. They have to be equivalent because they lead to things that are resonant structures of each other. The oxonium ion is resonance stabilized. Another word for this oxonium ion is called oxocarbenium ion. Carbenium is a term for carbocation. So this is an oxocarbenium ion because you got a positive charge on the carbon. These are two resonance structures of the same thing. Because oxygen's more electronegative than carbon, you assume that most of that positive charge is felt on the carbon. Sorry. So don't worry if you draw a mechanism like this and the answer in your text draws it like this. Those are two interchangeable, identical ways of drawing the mechanism. Any questions about that? All right. So then you can see where we're going when, in order to do mutarotation, we'll have water act as a nucleophile attacking the carbonyl carbon from below. If we attack the top resonance structure of the oxocarbenium ion, that's how we would do it. If we're going to do the same thing with the bottom resonance structure of the oxocarbenium ion, we would just draw one arrow this way. Now I've entirely run out of space, so we'll just show you the product of that, which has this OH2 group on C1. And then, of course, we can regenerate our acid catalyst with the conjugate base of our acid deprotonating at the oxygen, and that will get us to the alpha anomer. So you can do mutarotation either via a ring opened intermediate, or you can go through an oxocarbenium ion and attack it from below, and that'll give you the beta anomer. Yeah?
What will the percent yield be of each of the isomers?
So what is the percent of each isomer? Yeah, that's a good question. Anytime two stereoisomers are in equilibrium with each other, it's fair to ask, okay, what's the ratio between the two of them? And for two things in equilibrium, the only thing that determines the ratio between them is their relative stabilities. So let's actually answer that by asking, using your knowledge from 351, what do you expect to be better? To have the C1 hydroxyl axial or equatorial? Okay, you expect equatorial. What is the answer? Why is that true? A values and sterics. Okay, you've learned about that. So just as a reminder, you learned in 351, here is cyclohexane in its axial form. Here is methyl cyclohexane in its equatorial form. The methyl group is equatorial there. It's axial here. Now, it's not immediately apparent from the stick structure, but if we do space filling, you can see that that axial methyl group is bumping into other axial protons. Those are called 1,3 diaxial interactions. And you learned in 351 perhaps of things called A values, which tell you how much more stable the equatorial form, I'm getting it exactly backwards, how much worse in kilocalories per mole or in free energy the having a group axial is than having a group equatorial. Okay, so for an OH group, the A value in kilocalories per mole is about 1 kcal per mole. So if we were to predict what the delta G for going from beta anomer to alpha anomer was, we might expect it to resemble the A value. We might expect delta G for going from beta to alpha to be positive and to be basically the same as the A value for an OH group, which is 1 kilocalorie per mole. And we can use that information to predict a ratio of alpha to beta anomers using the relationship delta G equals RT ln K. Now, because this is not Gen Chem, we're not going to do that math. Somebody else has done it for us. We're just going to write it down. But we expect for if sterics is the only thing that's going on here, if sterics is the major factor, we expect a ratio of about, oh, get the number wrong, Ken, 75% beta and 25% alpha. Or in other words, 3 to 1. But in contrast, we actually observe about 67% beta and 33% alpha, more like 2 to 1. And so the conclusion is the alpha anomer is still not more stable than the beta anomer, but the alpha anomer is more stable than expected based on sterics alone. So that's weird. And in organic chemistry, we often say if it can't be explained by steric factors, likely it has to do something with electronic factors. By electronic factors, I mean considering electron density, electron delocalization. We'll say if it's not sterics, it's got to be electronics. So let's examine why the alpha anomer might be more stable than expected based on sterics alone. And to do this, we're going to zoom in on that alpha anomer and consider what's going on, particularly with electron density at C1. They're back. I learned some fun words this week from my young men. I learned about low taper fades. I already knew about Riz. I learned about a modifier for Riz, which is skibbity. I don't really understand that. And what else did I learn? I learned about how someone can be down bad for you. Have you heard that? Yeah, so I asked, so if I had a low taper fade and had a lot of skibbity Riz, would someone be down bad for me? They're like, yeah, or else you would crash out. So, okay. I really almost can't keep up. So crash out is a new thing. I asked my lab students a couple weeks ago if they'd ever heard of crash out. They were like, no. So maybe this is just barely, hasn't reached the, you should not be surprised when the nerds don't know the slang. Okay, well, that's all right. We know who we are and we're happy with it. Okay, where were we? Oh yes, the explanation for why the alpha anomer is more stable than expected. So, somebody once teased me about, a student once teased me about the class saying that if you don't remember what the explanation is and you guess hyperconjugation, you're pretty close. So remember, hyperconjugation is overlap of a filled orbital in a molecule with an adjacent empty orbital. And usually when we're talking about filled orbitals and empty orbitals, filled orbitals we're thinking of as non-bonding lone pairs, as an example, a sigma bonding orbital perhaps. The adjacent empty orbitals sometimes are empty p orbitals, but they could also be empty sigma stars or empty pi stars. And when an adjacent filled orbital overlaps with an empty orbital on the adjacent atom, the electrons in the filled orbital spread out a little bit. They don't totally populate the empty orbital, they just spread out a little bit. And the spreading out is stabilizing for the electrons. So The filled orbital that we're going to talk about is the non-bonding lone pair on the ring oxygen. The empty orbital we're going to talk about is actually the carbon-oxygen sigma star at C1. To draw that, you'd simply draw a node between oxygen and carbon. There are large orbital lobes pointing out away from the space between the two nuclei, and small orbital lobes pointing towards the node. There's change in wave function sign every time there's a node. There are nodes that I haven't drawn at the carbon and at the oxygen. You can tell they're there because the wave function sign switches as indicated by color. This is what a sigma star antibonding orbital looks like, and importantly, most of it, a lot of it, is pointing straight up 180 degrees opposite from the CO bond. And in that orientation, it overlaps perfectly with non-bonding lone pairs on the oxygen that are probably in sort of an sp3 hybridized orbital. I'm drawing it like this. There's another lobe here that I'm not drawing just to avoid confusion. Hyperconjugation is delocalization of electron density from the non-bonding lone pair into the sigma star. That's stabilizing, and that's why, and it's worth maybe 0.1, 0.2 kcals per mole, enough to change the equilibrium constant. In organic chemistry, we call this observation the anomeric effect, and we sometimes use it to help explain and predict reaction outcomes. Questions that students usually ask at this stage: isn't filling an antibonding orbital bad? Doesn't that break the bond? The answer is yes, if you fill it completely. If you don't fill it completely, if it's only partial mixing, then all it does is it moves the electrons in this non-bonding orbital to delocalize a little bit, moves them lower in energy, and then it actually moves the antibonding orbital higher in energy where it's less likely to be attacked by a nucleophile, overall stabilizing for the molecule. Okay, so that's the relationship between alpha and beta anomers, and you need to know that it's a combination of sterics plus the hyperconjugation that explains why the alpha anomer is more stable than you would expect. All right, yes?
For simple alkane, cycloalkane, in which there's not really hyperconjugation, would the percentages line up?
Yeah, so those A values, the question is, if this weren't an oxygen, if it were just a CH2 group, would the ratio be what was predicted by A values? The answer is yes. In fact, those A values were obtained from substituted cyclohexanes where hyperconjugation wasn't as big of a deal. Okay, yeah?
Can you go backwards so when you're switching, is it easier to switch back because the orbital is slightly filled so you can protonate that OH group easier and that bond will be weaker?
Is it easy to go back because of hyperconjugation? That's a good question.
From alpha to beta.
To alpha to beta. I don't know. Certainly it's observed, you can sort of see where the kicking off comes from, right? Because the lone pair is already hyperconjugating with the leaving group. So as soon as you turn that into a good leaving group, that's when the full-on kicking off happens. Yeah. The other thing I should point out in this story that I'm not going to draw, but I need you to imagine, that hyperconjugation is less of a big deal for the beta anomer. The sigma star antibonding orbital points 180 degrees away from the carbon-oxygen bond. It would be pointing down here, and whereas the lone pair is pointing this direction, they're not lined up with each other at all. So the key point is there is better, what I will call N for non-bonding lone pair to sigma star hyperconjugation in the beta anomer. Better N to sigma star hyperconjugation in the alpha anomer than the beta anomer. Okay. So next, we want to start talking about how to form acetals with carbohydrates. This is important in biology. It's also important in making candies. If you've ever made rock candy, you got to heat it up and you got to watch the temperature, and at a certain point, you start boiling and a lot of water starts coming off. What you're really doing when you make rock candy is you're making acetals out of carbohydrates. I don't know why that word says carbohydration. Sometimes my brain turns off. Carbohydration is not a thing. Somebody probably is selling a product out there involving carbohydration, and that is not a thing. Acetals with carbohydrates are called glycosides. And so we're going to talk about simple glycosides and then do some more complicated glycosides. If I took glucose, beta D or D-glucopyranose, and suppose I want to communicate that I know I'm missing the C1OH group. Suppose I want to communicate that I have a mixture of alpha and beta anomers. If I wanted to be super complete, I would draw both of them. But if I want to be lazy, there's something I can do to indicate a mixture of both. And that is a squiggly line halfway between equatorial and axial. Then you put an OH group on it, and that means both of them. Isn't that nice? That's fast, easy, communicates everything. So you're free to do that. Now, supposing that I put an alcohol in, and then a catalytic amount of an acid, say TSOH or some other kind of acid. I could imagine a lot of things happening, but suppose I supply an excess of the alcohol, and suppose along the way I'm removing water. Some of you will encounter problems like this and you're like, I have no idea what to do. And the problem is that you're just not connecting it to something you've done before a ton of times. You have to remember that the carbohydrate is a hemiacetal. And you have to remember that hemiacetals can convert into regular acetals by reacting with an alcohol. And when you did this before, the mechanism was simple. First, you would protonate the C1 hydroxyl with an acid. And actually, this is the same first step as that alternative mechanism for mutarotation. You protonate the C1 hydroxyl to turn it into a good leaving group. Then lone pair electrons kick down and kick off water to give you an oxocarbenium ion. Recall that this is the step that you are welcome to draw in sort of an SN1 resembling step where the water just leaves. Either way, you get a resonance structure of the same oxocarbenium ion. Just by tradition, I tend to draw it this way. Understand it is totally fine to draw it with the positive, with a sigma bond here and a positive charge on the carbon. Then you would show methanol acting as the alcohol, attacking the carbonyl carbon and breaking the pi bond. And then I'll have you finish that mechanism and draw what the product is. The product is going to be called a methyl glycoside of glucose. That's a dumb looking Y there. Try that again. Okay, that's it for today. We'll spend probably one more day on carbohydrates, and then on Wednesday we'll move on to a chapter on lipids.